you have seen in the previous video which we just played, you can see the breakage of droplets and rivulet, breakage of the stream, liquid, whether it is a matter or slag which was coming out. And not only that, you might have noticed this due to the drag of the gas, the high velocity by which it is coming from the tube, it is able to deflect even the ion stream and droplets and rivulets. And one thing is very clear from this video, that it is not a continuous flow. The liquid flow is not a continuous, it is certainly in discrete nature. So, one cannot apply the continuum theory or continuous flow theory to describe the liquid flow, especially in the blast furnace, and that which we had discussed before. And because this video which you saw is more related to the raceway, so we would be talking about the raceway now. So, in the blast furnace, due to the high velocity of gas at the exit of the tube, a cavity is formed which is called raceway, as the coke particles within that cavity are racing with high speed. So, the name raceway is coming due to the coke particles, they are racing inside the cavity, and that is why this name is given raceway to this cavity. And it is found that coke particles move towards the raceway as funnel flow. It is found from live blast furnace studies that some slag flow takes place inside the raceway along with some amount of liquid matter droplet, which you have seen just now in the previous video. However, towards the side of the raceway, more liquid viscous slag flow has been observed from live video. Of course, this was not there in the video due to some proprietary thing, but the dissection of the blast furnace in the live video shows there plenty of liquid which is flowing in between the two tubes or at the side of the raceway. So, the speed of the coke particle for different size in the raceway zone is shown in the next figure. So, you can see in this figure, this is the blast volume Newton normal per meter cube per minute. So, 3000, 4000, 6000, and the coke size, different coke size varying from 10 millimeter to 60 millimeter, and the coke speed in meter per second. So, one can see that when the blast volume or blast rate is low, the coke speed is not that much, but when the blast rate is high, which is sort of the trend in the modern blast furnace, in fact 6000 plus, the coke speed inside the raceway is quite high, and you are talking somewhere of this size of coke in the raceway. So, it is between 10 to 20 meter per second, and with this sort of velocity, when the coke particles are travelling, there would be a very high impact. So, at high gas flow rate, the speed is quite high, which will result in deterioration of coke quality due to impact, attrition, etc., and the formation of more fines near the raceway boundary. If there are more fines near the raceway boundary, it will block the space in between the coke particle. So, it will reduce the permeability and the pressure drop will increase, the operation of the blast furnace will become difficult, and that is the reason the lots of emphasis has been given on the coke quality. We need really very high coke quality, because coke is subjected to the extreme condition in the raceway region, and one do not want that it should create lots of fine or deteriorate or disintegrate. So, coke quality is at most important. So, this figure shows the distribution of coke particle near the raceway in a dissected blast furnace. As the particle size decreases, raceway expands more in vertical direction. So, you can see the raceway is expanding more in vertical direction than in the horizontal direction, and this is the tuya, and this is the cavity which what we call raceway, and the particles as you have seen even in the video, the coke particle was racing around this. So, just beside it there are large coke size particle, and away from this, so region 3 you will find a small brown type of particle which are lesser in diameter than this, and in this part in fact you get the dark dense layer. So, which is a mixture of graphite, metal, slag and small coke, and in this zone of course you get a large coke size particle again, and then in this zone you get dark angular large coke particle, and similarly at other places you get large brown and dark small particle, brown middle particle, brown and dark particle. So, mostly the small particle is just little away from the raceway after this large particle boundary. So, if more fines is getting created, it will block the voids in between, and then the easy passage of gases which are coming out from the raceway would be difficult. So, pressure drop would be high, and operation of the furnace would be difficult. This shows sort of a vertical view of the TS section of the blast furnace. Again it is a of the dissected live blast furnace. As you can see, different types of coal surrounded actually around the raceway, and so essentially it is the same thing which is given on the top view of the dissected blast furnace in the raceway region. So, one thing is very clear that this region is quite important for the distribution of the gases or the reaction which is taking place, which affect the whole blast furnace in the upper zone and even the lower zone of the blast furnace. So, the burden descent is controlled by the shape of the raceway. Larger the raceway, more will be the charge movement and uniform gas flow. Therefore, productivity of the furnace is proportionate to the raceway size and shape. If the raceways are smaller and confined to the periphery, charge will result with cold hearth and frequent burning of the tuya. So, deeper the raceway penetration, that is furthest the point of CO2, and thus the point of highest temperature, lesser would be the hearth heat losses. So, this you can see this has not reached even at the middle of the blast furnace. This is a very small in comparison to this, the raceway size. So, really if you want a good sort of flow of the gases which are coming out from the raceway, what you need to increase this. So, deeper penetration, so that gas can come and can go up to here and distribute themselves and can react with the charge in the upper region, as you can see in this one. And so, more penetration of this or bigger size of the raceway means better distribution of the reducing gases and better production of the blast furnace productivity is going to increase. So, it is directly affecting the productivity, and that is why the shape and size of the raceway is very important in the blast furnace, like a heart of it, and lots of study has been done or devoted only on the raceway investigation. About this reaction, we would be talking a little bit in the coming slide. So, it is found that coke and fuel is burned first to form CO2 inside the raceway, where the oxidizing atmosphere prevails. So, remember inside the raceway CO2 is formed because you are injecting air which has or even if you are injecting a oxygen rich air, then you would be having more than 20% oxygen in the gas, and you have some carbon. So, carbon in form of coke is less. So, essentially it forms CO2 because there is a deficiency of the carbon. So, inside the raceway, but as it comes toward the periphery of the raceway or the boundary of the raceway, it comes in contact with more coke. So, immediately it forms CO. So, this CO2 is reduced to CO as it approaches the raceway boundary, coke filled area. So, inside the raceway is a oxidizing atmosphere sort of, and then it becomes reducing up to that. So, during the oil injection, reaction shifts to the CO rich side, because oil has many other components, methane and carbon content components. So, you get the carbon inside the raceway. So, that is why reaction shift to the CO rich side as heavy oil burns at the tuer nose and consumes oxygen. So, these results are shown in the next figure. So, if you look at this figure, so in this one we have distance from the furnace wall. So, this is actually tuer. So, away from the furnace wall, you will see this is the boundary of the raceway, and this is the gas temperature. You can see the gas temperature is increasing. So, as long as CO2 is formed, that is a exothermic reaction. So, gas temperature is increasing, and as soon as CO starts forming, which is more endothermic, the temperature drops down at the boundary, and you can see in this one the distribution of the various species. So, this is CO. So, you can see almost negligible CO till the raceway boundary. So, this is the figure when blast is having only air. So, as soon as it reaches near the raceway boundary, more carbon is available. So, CO2 reacts with more carbon, forms CO, and suddenly CO shoots up, and inside the raceway CO2 is forming, and as it reaches near the boundary, CO2 decreases tragically and reaches almost to 0. So, that is how this is more oxidizing atmosphere inside the raceway, but outside it is more reducing. However, if one uses the oil, fuel oil along with the air, then because the carbon is already there in the fuel oil, so it will react with that extra carbon. So, CO will start forming. So, that is a fuel oil. So, now even inside you can find that some percentage of CO in the raceway, but of course, more carbon is available at the boundary. So, CO concentration increases quite high at the boundary again, but CO2 concentration is not as high as it was in the pure air case. So, that goes to a little peak and then it comes down. So, here it is about 10%, but in this case it is about 18% or so. And similarly, the temperature, as I said, the CO formation is an endothermic reaction, it needs takes more heat. So, temperature actually highest temperature actually shifted more within the raceway, because as more carbon is available, it starts reacting, and so temperature within the raceway starts dropping down. So, which shows into this figure. So, during oil injection, the reactions are, so this is with the air and this is with the that CO2 is reacting with the carbon, and that carbon, it could be at the boundary or it could be some other source like fuel oil and other thing. So, this is a highly endothermic reaction. So, it needs heat, so flame temperature decreases as CO formation occurs, which we have seen in the previous slide. So, raceway adiabatic flame temperatures, this what is called raft has already been defined or mentioned before. It is again reproduced here. So, raft or a flame temperature, in short what we call just a flame temperature, is given by this, which was given before, and I think all the nomenclature and other thing has been given in the previous lectures. So, you can go through that and you can find out all the nomenclature. So, as soon as carbon, oxygen and water are converted to CO and hydrogen within the raceway, the temperature prevails at that point is known as flame temperature. So, the effect of different parameter on raft is shown in the next table. So, just pay attention on this. So, as soon as carbon, oxygen and water are converted to CO and hydrogen within the raceway, the temperature prevails at that point is known as the flame temperature. So, this is quite important and it should not exceed to certain limit, and the effect on flame temperature of various factors is given here. So, as you see, if we increase the blast temperature by 100 degrees Celsius, our flame temperature increases between 60 and 80. 1% increase in oxygen in the blast air or whatever it is gives rise to 45 to 50 degrees Celsius in flame temperature. Similarly, 1% moisture in the blast, because certainly moisture will reduce it will not increase. So, it reduces the flame temperature between 40 and 45, and if a higher percentage of this, then it reduces to that. Similarly, the natural gas. So, 1% or 100 meter cube per ton of hot metal is introduced with the blast, then it reduces the flame temperature tremendously. In 1%, 45 to 55 in that range, and 100 meter cube per ton of hot metal 320 to 450. So, that is a huge decrease in the flame temperature, which is not desirable. So, certainly when natural gas we will see even few other like coke oven and oil, this all should be used along with oxygen to maintain the blast or flame temperature. So, coke oven gas, again of the same order natural gas you put it, it has a little lesser effect, again nevertheless it is a very big effect having on flame temperature. So, between 200 and 250 it reduces the flame temperature. Oil, again 100 kg per ton of hot metal reduces the flame temperature in the range of 270 to 340 degrees Celsius. Pulverized coal, which is quite prevalent, pulverized coal and oil are quite prevalent in the blast furnace to use along with the air blast air. So, low volatile pulverized coal, if one uses about 100 kg per ton of hot metal, it reduces the flame temperature between 0 to 130 and high volatile between 150 and 220. So, all of these should be accompanied with the oxygen in order to maintain the flame temperature. So, this is just giving you an idea how these various injectors with blast air may affect the flame temperature. In fact, nowadays even some municipality waste, plastic, these are also being used. So, same sort of effect they can have in a big range. So, all of these have to be used along with the oxygen in the blast to maintain the flame temperature. So, due to importance of raceway in blast furnace, maximum attention has been paid to study it and to predict the size and shape of it. As I mentioned before, that size and shape of it are directly related to the productivity of the blast furnace. So, these are very important parameter. So, it has already established that raceway formation is more or less a physical phenomena rather than a chemical one. So, that has been found that it is more like a physical phenomena. The higher the velocity, probably you can have a good size of raceway and maybe even shape. So, it is not that much dependent on the chemicals. So, it is more a physical phenomena. The very old relation to predict the raceway diameter is given by this. So, where dt is the tuyere diameter and Rf is the raceway factor, which is expressed again from this. So, rho g is the gas density and rho k is the coke density. G acceleration, V is the volume of the Bose gas in normal meter cube per second, and A is the cross sectional area of the tuyere. P and P naught are the atmospheric and standard atmospheric pressure in kg per centimeter square. Dk is the coke diameter, and Tg and T naught are gas temperature in front of the tuyere and standard temperature in degree Kelvin. So, as I mentioned, because the size and shape is very important of the raceway to know the performance of the blast furnace. So, many attempts have been made and this is just one of the expression very old, almost 40 years ago was sort of proposed and it is written there, but lots of work has been done after that. So, raceway size and shape is affected by blast volume, velocity, temperature, coke particle size and shape, tube diameter shape and its inclination, tube protrusion inside the blast furnace, intertubule spacing, Worden movement and void fraction of the coke bed. So, there are host of factors on which the raceway size and shape depends. So, there is one problem now. So, a blast furnace which produces 3000 tons per day of hot metal operates at 1500 normal meter cube per hour blast rate. The total number of tears are 20. Determine the gas velocity at the raceway boundary if the equivalent diameter of the raceway is 2 meter or 0.5 meter. So, two cases, some of the blast furnace they have a that sort of even raceway diameter, and many of them operating at high productivity have this sort of diameter. So, we know in the solution total blast per day would be we know 3000 ton, that is the per day the productivity, and blast rate is 1500. So, total blast per day would be multiplying these two, that will give you the normal meter cube per day. And blast rate per second, which if we convert that, that is going to give you 52.08 normal meter cube per second for 22 years. So, this is actually for 22 years, as it says the total number of 2 years are 20. So, this is also the total blast rate. So, V naught is the velocity of the gas at the raceway boundary we assume, then normally you can have it a volumetric flow rate, which is nothing. This should be equal to the area into the velocity at the raceway boundary. So, we can calculate the velocity at the raceway boundary. So, Q is 52.08. Now, we are doing at the raceway boundary. So, there would be a 20 raceways. So, naturally we are talking about the 1 tier. So, this has to be divided by 20. So, which we have done it here. So, that would be sort of a volumetric flow rate from the 1 tier and divided by the area of the raceway. So, in the first case it is 2 meter given. So, pi r square. So, that gives you the velocity which is coming out from the raceway boundary is 0.83 meter per second. Same calculation if we do it for the second case, then it comes 13.3. So, it is more than 1 order magnitudes high than the previous case. So, you can understand how much difference it is going to make. This high velocity can create a very a big problem in the blast furnace. This is crossing the fluidization velocity of the coke and coming near to the eluteration velocity of the coke. So, that will give sort of a not a smooth operation in the blast furnace than this, and certainly the Reynolds number would be very high in this case. So, that tells you a little idea how the size is going to affect the velocity which of the gases by which they are coming out through the raceway boundary.